Hello, welcome to this pre-lab video that we are looking at lab V14, the Electromotive series. And interesting thing about this particular virtual lab is that in large part it covers a number of concepts that you already have talked about in Chem 105. So this is kind of a bridge almost, if you will, between some stuff that we learned in General Chemistry 1 and some stuff that you're going to learn in General Chemistry 2. And of course, we're talking about redox reactions. Now, in Gen Chem 1, Chem 105, we talk about redox reactions in terms of recognizing when electrons are moving and identifying oxidizing agents and reducing agents. And we even talked a little bit about the idea of oxidizing and reducing power, looking at when stuff reacts versus when it doesn't. Well, the purpose of this lab is to go through and do some of those kinds of things. And so what I'm going to do here is a good chunk of this lab is all about balancing redox reactions and recognizing when they come. I'm going to refer you to other videos in my video series for those purposes, mainly because there's no need to rehash any of that stuff here. You probably just need a decent sized reminder and a refresher on those. So in the description of this video, I will put a couple of links to some of my other videos. Now, if you are one of the people who learned how to balance oxidation reduction reactions using the oxidation number method, that will serve you very well for questions like 2A and 2B here. One thing I will caution you on, however, is that when you start to bridge over into electrochemistry, chapter 17, there is going to be a need to know how to look at half reactions. And in particular, the half reactions that we usually look at are reduction half reactions, which can be found by taking any reaction and manipulating it so that the electrons are being gained instead of lost. So if you do not have any familiarity with the half reaction method, I would encourage you to give that video I did on the half reaction method a second look. Now, for those of you that have been balancing using that method, you're actually all set. You just have to go back and remember how to do it. But before we talk about the lab itself, I just want to kind of give some background information for kind of where this is coming from. And it's a relatively simple concept. It's actually simple enough that it's not really in my Chem 105 notes. I'm actually going to my Chem 100 notes for this. Because what we are talking about essentially here is an application of, in what are large cases, single replacement reactions. And for that, we get into something called the activity series. Now, we've talked a little bit about activity series in the sense that we know that some elements are more reactive than others, some metals are more reactive than others, some are much more likely to give up their electrons than others. And so you can see at the top of this list, you've got things like your alkali metals and your alkaline earth metals, your potassiums, your sodiums, your calciums, your bariums. These all react really violently with water and will replace the hydrogen in water with virtually no input whatsoever. These ones here require steam to get a chemical reaction with water. So obviously we got something more energetic going on here. These ones will only displace hydrogen if the hydrogen is in acids. And these ones down here are inert toward hydrogen and will not replace hydrogen regardless of what kind of medium it is in. So that's kind of what we're going after in this, but on a larger scale. We're going to go beyond just looking at metals. We're going to look at how do metals react with each other? How do nonmetals react with each other? How do they interact with each other? If I have an elemental sample of iodine and a sample of iron, will they react with each other? or will they just kind of sit there with each other and not actually react? That all has to do with their oxidizing and reducing potentials. So as we look at this pre-lab, we can see that some of the questions here are along those kinds of lines. Number one, looking at what kinds of observations can we make that would determine whether a reaction has occurred or one hasn't occurred. And this is kind of like chemistry 101 here. This is, what are the things that would tell us that a reaction is taking place? We'd be looking at things like color changes, evolution of a gas, evolution of a solid, changes in temperature, all of those kinds of things. Number two asks us to balance these equations and identify what was oxidized, what was reduced, and what the oxidizing and reducing agents are. Again, I'll refer you to those YouTube videos in the description. That will help you do that in, regardless of what method suits you the best. And then this last one here is kind of a mock-up of what you're going to do in this lab itself. And what I mean by that is you are going to ultimately rank these three substances, these three chemical reactions in terms of their reactivity based on what ones are best suited to reactions and which ones are the worst suited to the reactions. So what we're looking at here, we're looking at reduction half reactions. We would be looking at the hydrogen ion adding electrons to become hydrogen. We would be looking at the calcium ion adding 2 electrons to become calcium metal. And we would be looking at the lead-2 ion becoming lead. So those are the 3 half reactions that we are going to use. Our job is to put them in the correct order based upon their oxidizing strength. The stronger it is as an oxidizer, the more likely it is to be reduced. So based on those observations, which one is the most likely to add those electrons and which one is the more likely to actually reverse the process and give electrons away. The one that is the most accepting of electrons is the strongest oxidizer. The one that is the least accepting of electrons, the most willing to give them away, that's going to be your weakest oxidizer. And then the one in the middle is, well, the one in the middle. So that's what you're doing here in number 3. Now, as far as the procedure itself is concerned, this is actually a relatively straightforward procedure. Once again, you're going to go to the Chem Collective bench. And so just Control-click will open this up. You've got all of the solids. We've already preloaded the activity here for you. So you don't have to go to File and Open or anything like that. But what you're going to do is you're going to follow this protocol where you make each of these solutions and you record in the data table what happens in each of those cases. So for the first set here, you are going to take copper ion solution, 0.1 molar copper 2+. So I'm going to find that one right here. And I am going to replicate it. So I now have 3 of these. And to one of them, I am going to add silver. To one of them, I am going to add zinc. And to one of them, I'm going to add lead. So let's start with the silver. We also need the zinc and the lead. So in the first one, I need to add 0.5394 grams of silver. And now I can see the results of what happened. And so in this particular case, I look at this and I say, the concentration of the copper did not change. Concentration of the nitrate did not change. I have just as much undissolved silver as I did before. And I've got just a little tiny speck of copper in there, probably not enough to measure. So in terms of my data, I would write down these things that I saw. And based upon whether or not I saw anything change, I determine whether or not a chemical reaction occurred. So in the case of the copper and the silver, it doesn't look like a whole lot happened there. For the copper and the zinc, again, I'm starting with 0.1 molar copper, 0.2 molar nitrate. I put in 0.3269 grams of zinc. And I notice a couple of things. First of all, the solution is no longer blue. And secondly, I can see that my copper concentration has basically become zero. My zinc concentration has effectively changed as well. And look at my values here. They're kind of fluctuating a little bit, but I can see that I've got virtually no zinc metal left in this solution, in this flask, and I've got about 0.32 grams of copper. So lots of things changed here. That would be evidence of a chemical reaction. And then finally, 1.036 grams of lead into this last one. And I see a similar kind of result. The copper concentration has definitely decreased. The lead, it's still stabilizing, but the lead is effectively zero. The copper metal is increased in value. The lead has effectively replaced the copper. So I would have evidence of a chemical reaction there as well. So what does all of this mean? Well, what it means is that copper 2 plus was a pretty good oxidizer. Copper 2 plus forced the oxidation of the zinc. Copper 2 plus forced the oxidation of the lead. So if I was looking at this from a perspective of status, I would look at this and say, okay, the silver ion is better than the copper 2 ion at being an oxidizer, because if copper was better, it would have oxidized the silver, which it didn't. And we know that the copper is better than zinc and lead. But at this point, we can't determine anything about zinc versus lead. All we know is that both of them reacted with copper 2. So I can start visualizing an activity series around this, starting with the silver ion on top, copper underneath it, and zinc and lead somewhere underneath copper. Again, we don't know the order yet because we haven't tried to react them with each other. But this would be the start of our activity series. And you can see that as we progress through this, you're going to do a series of extra tests that are going to essentially verify each other in the long run. You'll do similar kinds of tests with the halogens, chlorine, bromine, and iodine. And then we have given you data for the interactions between bromine and silver, chlorine and copper here in part 3. Based on these data, you should be able to determine whether or not a reaction has occurred, and you can kind of see where the two tables mesh with each other. This is going to lead you to building an activity series based upon the metals first, then the non-metals, then where they come together. And based upon this activity series, you'll answer the post-lab questions that'll say, okay, I've got this reacting with this. Does anything actually happen? And if it does, show me what you expect to happen. And that's the direction that you're going to go with this particular virtual lab. So kind of short and sweet with this particular pre-lab and walkthrough. I don't anticipate too many problems. We have done the simulation in the past. It has worked out pretty well when we did. The hardest part with this one, honestly, is just the interpretation, trying to figure out and make sense of, well, this reacted with this and this reacted with this, so what does it all mean? But those are the kinds of questions that can be addressed during the lab while your classmates are working on the other experiment for this week. So without any further ado, I'm going to call this particular video to a close. Have a good day.